Hello there. So today we will be talking about concentration terms. This is a second lecture in the fundamental series after mole concept. If you have not learned about mole concept, I suggest you go learn that one and then you can come back and learn about concentration terms. So do you know that how much glucose is present in human blood under normal conditions? The blood contains about 90 mg of glucose per deciliter, and deciliter means 100 ml. How much salt is present in saline drip intravenous? Saline drip is something which is given intravenously when someone loses lot of body fluid, right? And this body fluid is lost in form of vomiting or diarrhea. So it is to replace the body fluid loss during such condition, and it contains about 0.9% sodium chloride solution in water. All right. Now, how much is the toxicity limit of arsenic in drinking water? So the answer to that is 0.01 ppm. ppm stands for parts per million. And what is the molar concentration of 37% weight by weight hydrochloric acid? So the answer to that is 12 molar. Now if you look at these terms, okay, these are called concentration terms. Let's look at what is concentration. So concentration is amount of one substance present in 1 unit of another substance, and this the another substance what here means is it's usually a solution, right? Now in the previous slide we have seen that the amount of glucose present in blood is about 90 mg per deciliter, right? That is the normal range. So 90 mg present in 100 ml of blood, right? Now, so the question is why concentration is required. If I ask someone to determine how much glucose is present in blood, and I give this to 3 of my students. Now first student, okay, he used a very efficient technique and he utilized only 20 microliter of blood, and in which he found that there was about 18 microgram of glucose. The second student, he was bit more generous and he thought maybe I can use 1 ml blood, and he found out there was about 0.9 mg glucose in 1 ml. The third student, and he used 10 ml blood, okay, and he determined that 10 ml blood contains how much? About 9 mg glucose, right? Now which of these is correct? If you look at these numbers, you will see superficially on the surface that these are different values, right, present in different volumes of blood. But if you calculate, you see that these all represent the same 90 mg per deciliter of blood. So, the point here is the concentration terms is useful to simplify when different volumes are used for measurements, right? Now, there are different ways of expressing concentration, such as percentage quantity, where we have weight by volume, weight by weight, volume by volume, and then we have some standard ways of expressing concentration: molarity, normality, molality, parts per million, and in the lecture we will see some calculations as well. Now, before we dig deeper into this, let's cover up some basics like what is a solute, what is a solvent, and what is a solution. Okay. Now, if you have what we have seen earlier, that in saline drip there is 0.9% salt solution is called saline drip. Okay. Now, in order to prepare that, we have components NaCl, which is our salt. Okay. Then we have water, and you mix this in certain proportion and you get saline drip, right? Now, out of these things, this is the mixture where we have added salt and water. So, this will be called solution, right? And out of these two components, the one which is of larger quantity or major quantity is called solvent, and the one which is lesser quantity or minor quantity will be called solute. Okay. So, that is the general rule of which is the solute or solvent in a given solution. Okay. Also, the physical state of solution, because solvent is the major component, will be governed by the physical state of the solvent. So, in this case solvent is liquid, then solution will be also liquid. All right. So, these are some basic things which you have to remember. All right. Now, moving forward, let's look at percentage terms. Percentage terms usually are of three types: percentage weight by volume, percentage weight by weight, and percentage volume by volume, right? Now, let's look at each of them one by one. So, percentage weight by volume, right? So, weight means obviously it's solid. Is this yellow? It's supposed to be orange, but it's looking more like yellow. And volume is obviously the solvent part is liquid, and obviously the solution here will be also liquid, right? So, how it is calculated? So, percentage weight by volume is calculated by amount of solute in grams divided by volume of solution. Remember this, it's solution, not solvent, multiplied by 100%, right? So, that will be your percentage weight by volume. Saline drip, okay. How much was it? It was 0.9% weight by volume. Salt solution is saline. That means 0.9 gram of salt is present in 100 ml of solution. Now let's look at percentage weight by weight. So percentage weight by weight can be solute and solvent, both can be solid, both can be liquid, and in one case solute can be solid and solvent can be liquid. Percentage weight by weight is usually used for viscous solutions such as glycerol, right? Or it can be used for concentrated HCl, right? Now let's say I have to make 5% weight by weight of glycerol in water. So the solvent will be water, solute is glycerol. So this is an example of where both the phases are liquid. So how do we do that? So we take 5 gram of glycerol, right? And total weight of solution will be how much? Solution weight is 100, right? By definition of percentage weight by weight. So therefore solvent will be how much? 100 minus 5, that is solution weight minus solute weight, right? Because solute and solvent gives you solution, right? So 5 gram of glycerol will be added with how much solvent? 95 gram of water, and this will give you 5% weight by weight glycerol. Alright. Now let's look at the third one, which is percentage volume by volume, right? Now obviously the both phases are liquid, and let's say you have to make 5% volume by volume of ethanol. How do we do that? So for that you take 5 ml of ethanol, right? And you add water to make final volume of solution, how much? 100 ml. Now this is slightly different than what we have seen in this case, okay? Now let me explain you this further, okay? So how to prepare a 500 ml solution using volumetric flask? What you are seeing here is called volumetric flask, okay? So this is a glass apparatus which is used to measure fixed volumes, okay? So let's say for 100 ml you will have a different volumetric flask, for 200 it will be a different volumetric flask, and similarly there will be a whole range of volumetric flasks used in the lab. Now how do we use it? So you fill solution, and you are seeing this blue line here. Let me zoom it a bit. This blue line, what you are seeing here, that is the mark up to which you have to fill to get 500 ml volume, right? Okay, so we have to prepare 5% sucrose solution, okay? Now how do we prepare 500 500? So how do we prepare 5% weight by volume of sucrose solution? Now, so obviously 400 ml, let's do it like this, you need 5 gram of sucrose. For 500 ml, obviously you will need 25 gram of sucrose, right? Now so this is just a physical representation of 25 gram of sucrose. Okay. So how do we do that? How do we measure, how do we prepare this solution? So there are two ways of making it, and one of them is wrong. Okay. And which I have seen students in their early graduation level or even in school level, I have seen people doing this mistakes. So pay attention to this one. So how do we do that? So the wrong method is, I'll tell you which one is wrong. You add sucrose to it, obviously. So let's make that physical representation here. So this is your sucrose added to the volumetric flask, right? And in the next step, so first is weigh and add 25 gram of sucrose, and in the next step, okay, you measure 500 ml of water with, let's say, a measuring cylinder. Okay, and then you add this to this one. Now this method is wrong. Okay, so what is the correct method? So we have weighed and added 25 sucrose here, 25 gram of sucrose here, right? And in the next step, so the correct method is, first you weigh and add solute to, so I am writing solute so that you can generalize the same method for any solution you prepare in your lab. So you weigh and add solute to volumetric flask. In the second step, you add your solvent. In this case, it is water. Now, how much to add? So generally, whatever is your target volume, you add about 70 to 80% of that volume. Okay. Now in this case, 70 to 80% will be how much? It will be approximately 350 to 400 ml, right? You don't need to be specific, you can just be in the ballpark. So you add solvent, in this case water, and you fill it somewhat up to here. You have filled it. In third step, you dissolve it completely. Okay, dissolve completely. Okay, and in the next step, you add water to make up volume, right? So you add more water and you fill it up to this mark, up to the blue line, and finally you close the lid and mix it properly, right? You mix it completely, and now you have a 5% sucrose solution of volume 500 ml. All right. Okay. Now, what about 20% sucrose solution? How much sucrose will be needed for this month? This much. You can pause the video, calculate and come back. Right. So the answer will be 100 gram of sucrose. Now the question is, why this method was wrong? Okay, why was this wrong? Now the thing is, when you add a solute or when you dissolve a solute, it will occupy some volume. So let's say this 25 gram, let me change color for this. Which color? Let's take blue. So 25 gram of sucrose in dissolved state has a volume of, let's say, x ml, right? So once you have, so by this method, okay, this one, this is wrong method, okay. By this wrong method, if you do, what will you do? So you have a beaker, okay, and you add 25 gram of sucrose, okay, and then you add how much volume of water? 500 ml, right? But the thing is, this 25 gram of sucrose will also have its own volume, which we are supposing x. So what will be the final concentration? You have solute will be 25 gram and it will be dissolved in 500 ml of solution plus x volume, which is coming from the solute itself. Now, because this denominator is going higher than 500 our target, that means this whole value will be finally lower. So our concentration will be lower than our goal. And what was our goal? 5% weight by volume. Alright. So that is the reason why this method is wrong, and you have to always follow this method. Okay. There's a question I wanted to ask, and let's see if you can answer this one. Between these two solutions, okay, which of them has higher concentration of water? That's the question, right? Figure that out. Answer is this one, and find out why. Okay, this is important, especially when we'll talk about transport through membranes in lectures ahead, especially when we start learning about biological concepts. Okay. Now let's look at addition of concentration terms. Alright, so I have asked two of my students to make 5% glucose solution, right? And one of them made about 200 ml of 5% weight by volume, and the other one was a bit more generous and he made 300 ml, right? Now I have asked them, okay, why don't you mix the both and let's make it a single solution. Okay. Now, what will be the concentration of this final 500 ml solution? The answer will be 5% only. Okay. Now, why, if you want to calculate, let me explain you in another example. Okay. So this time I asked both of them again, okay, make this again. Okay. Make this 5% glucose solution. Okay. And this time the first student, he didn't want to calculate anything again, so he made the same thing again, right? And the other student, he was like, okay, maybe I'll be bit more generous and make 10% weight by volume of 300 ml, right? And this time also I asked them to mix them again, right? Now how much will be the final concentration of this 500 ml solution? So the easy way to calculate this is find how much is total solute and divided by total solution volume, and obviously you multiply this by 100%, right? So in the first case, which is 200 ml of 5% solution, right? So 5% means 5 gram in 100 ml. So 200 ml will have how much? 10 grams, right? So 10 gram glucose was measured by first student, right? What about the second one? 300 ml of 10%. How much is this one? So let's calculate this one from the, let's reinforce your practice. So how do we calculate percentage weight by volume? We calculate amount of solute in grams divided by volume into 100, oh, real space problem, 100%. Okay. So he has made how much? 10%. Amount of solute, this is what we want to find. Okay, let's call it X. Volume is how much? 300 ml, and obviously 100%. Right. So from calculating this, you can find that X is equal to how much? 30 grams. Right. So this next student, the other student weighed 30 grams, and total solution volume will be obviously 500 ml. Right. So it is 40 grams and 500 ml. Now if we want to finalize our answer in terms of percentage weight by volume, then we have to multiply this by 100%. So answer will be how much? It will be 8% weight by volume. That is your answer. Okay. This same answer can be also given in terms of what? In terms of, let's say, gram per ml. Okay. So for that you don't need to multiply by this, and you can simply say answer will be 0.08 grams per ml. How do we do? Yeah, it's simple, right? You divide 40 gram by 500 ml and you get this. Okay. So there are two answers for this. Depending on if you have a multiple choice question, you can answer in format of this and you can answer in format of this, right? And using the same procedure what we have done here, you can just cross check whether this 5% answer is correct or not, right? Now let's look at molarity. Okay. So molarity is number of moles of solute dissolved in per liter of solution. Okay. It's solution, not solvent, right? So the formula of molarity is, let's change it back. The formula of molarity is number of solute moles divided by volume of solution. And if you are not familiar with moles, you can simply check my previous video where we have talked about mole concept, right? Go and watch that. It will help you understand mole concept. Okay. So And if you are not given how many moles of solute are being weighed or are in the question, you can always calculate from weight of the solute divided by molecular weight of solute multiplied by volume of solution. This will be in liter, this will be in grams, this will be also in grams, right? So this entity itself here will tell you how many moles are present. Now, how to prepare 500 ml of 1 molar NaCl solution? Okay, you calculate that and let me know. Okay, it's a easy one. So I'll tell you molecular weight of NaCl is 58.5 grams per mole. So this much 58.5 gram will be required for 1 liter of 1 molar solution. Therefore, for 500 ml you can half it, and that will be your answer, 29.25 grams. Okay, and obviously this will be prepared like what we have seen, the use of volumetric flask, right? All right. Normality. So normality is number of equivalents available for reaction per liter of solution. Now equivalent means reactive capacity. Okay, equivalent means reactive capacity. Now that also tells us that it is useful during reactions such as acid-base reaction. Okay. Now in modern science, it is finding its use less and lesser, but still it's good to be aware of. And for example, let me give you an example. So HCl, okay. So if we prepare 1 molar HCl, now reactive capacity means how much H plus ion, acids obviously will give H plus ion. How much S plus ion will be released by this HCl? Well, it will be same as the whole, because each molecule of HCl will give out 1 H plus. So that will be 1 normal HCl. But this will be different in case of, let's say, H2SO4. So 1 molar H2SO4 will be equivalent to 2 normal H2SO4. I think you get the point now. What about H3PO4, phosphoric acid? 1 molar H3PO4 is equivalent to 3 normal of H3PO4, sorry, PO4. Alright, so this is normality. Okay, moving on to the next one, parts per million, also expressed as ppm. Okay, and it is used when expressing trace quantities. Trace quantities means very less. Okay, now if you have noticed, I have expressed the toxicity level of arsenic as 0.01 ppm. Okay, now what is ppm? So ppm will be expressed as number of parts of one component divided by total number of parts of, okay, all parts of solution and multiplied by million times power 6. Okay, so what does it mean? So if we try to understand this one, so that means if we have 0.1 let's say grams, okay, now if you know the density of water, 1 gram is equivalent to 1 ml So 0.01 gram, okay, and if it is in 10 power 6 ml, so this will give you 0.01 ppm, right? Okay, now 10 power 6 ml is equivalent to 0.016 gram 1000 liters, or you can convert this into milligrams, and you can say, and we can say 10 milligrams per 1000 liter, or we can also say 10 microgram. I have divided this by 1000, so I have to divide the denominator also by 1000, and it will be 1 liter. So 0.01 ppm is equivalent to 10 micrograms per liter. All right. Okay. So that's the conversion. If you have to convert 0.01 ppm to micrograms per liter. Okay. Moving on to the next one, we have molality. It is denoted by M. Okay. And how it is defined? Now this one is different than the rest because the moles of solute are added in 1 kilogram of solvent. Okay, and weight is taken in the denominator. Now the moment weight comes into the picture and volume doesn't, that means not affected by temperature, right? Because we know if the temperature is high of the solvent, in case, for example, in case you are measuring molarity, okay, you are preparing using molarity, and you are preparing, let's say, 5 molar NaCl. It's too high, but okay, for the sake of conversation. And then you have to prepare, and you have to add water at, let's say, 60 degrees Celsius, because obviously this is very concentrated. You may have to have a higher temperature solvent so as to dissolve the NaCl, right? Now at this temperature, okay, the volume you measure will not be equal if you measure the same volume at 25 degrees Celsius or at 4 degrees Celsius. And since volume will differ, right, if the volume differs, that means the molarity will differ. Okay, so the molarity is dependent on temperature, okay, whereas molality is not affected by temperature. So that's the advantage of molality over molarity. All right. Okay. So yeah. So the question from previous lecture, before we go on and talk about the questions for practice, I'll give you some questions for practice. Again, if you have not read mole concept, you can quickly brush up your mole concepts in the previous lecture of fundamental series. So the question which I had given earlier was, if all the molecules of 18 gram of glucose are converted into maltose, how much maltose will be formed? So the hint what I have given was, this is the molecular formula of glucose. Okay. Now how does maltose form? It forms from 2 molecules of glucose, and it forms C12H22O11 and 1 molecule of water. So we have seen that from the stoichiometry itself, 1 gram If you don't know about stoichiometry, again watch this chapter. Sorry, 1 mole forms 1 mole of maltose and 1 mole of water, right? So when I say 18 gram of glucose, that means 9 gram of glucose will react with 9 gram of glucose, or we can say 2 moles of glucose gives 1 mole of maltose, right? That means 18 grams. Okay, now the molecular weight of glucose you can calculate from here. It will come about 180 grams. That means 18 gram will have how much? 0.1 mole, right? That means 0.1 mole will give how much maltose? 2 moles are giving 1 mole. So 0.1 mole will give 0.05 mole of maltose. So far so good. You can easily calculate how much is the weight of 0.5 mole maltose. Okay. 1 mole maltose weighs about 342 grams. So 1 mole of maltose weighs 342 grams. That means 0.05 mole will weigh 17.1 gram. So that much maltose will be formed if 18 gram of glucose is completely converted into maltose, then the weight will be 17.1 gram. And where the remaining, because mass conservation is there, you remember, you can see that 18 gram is converted into, let me change colors. Okay, so 18 gram is converted into 17.1 gram, but because mass conservation is there, where thus this 0.9 gram has gone, this is gone to form 1 mole of water. Okay, not 1 mole, I am talking about the stoichiometry. It will be equivalent to same concentration as maltose, that is 1 mole, which is 0.05 mole of water will be formed, right? So water has a molecular weight of, now let's say molecular weight of water will be how much? 18 grams, right? 2 plus 16, that is 18 grams. Okay, and then you multiply, so that means 1 mole is equivalent to 18 grams, then 0.05 mole will be how much? 0.9 grams. That is what the weight difference was. All right. So I have some questions for you to practice. What is molarity of 10 ppm NaCl? It's easy. You can always, you can use molecular weight, and I mean, we have covered the concepts. You can easily calculate. And this is obviously an easy one. How much glycerol needs to be weighed to get a 5% weight by weight solution, right? So this is a good one. This is okay. You can try this to gain confidence, and then you try this one. All right. See you in the next one. Be safe. Have fun. Bye-bye.